Today talk is very different from all my research and very different from all other talks, and it represents work we are doing as with support with ISTRC, but it's in conjunction with work being done as part of European Horizon Consortium on exploring effects of electromagnetic waves on human being. And in particularly, we are investigating how these electromagnetic fields within the vehicle influence the driver and the passengers. And then more specifically, we are investigating its effect on the red blood cells. And I explain you why. And this work is done in collaboration with Hebrew University, a big team of Yuri Feldman laboratory, and Anna Bogdanova from Zurich University. So the background is clear, but not obvious for everybody, that there is a growing number of electromagnetic sources that influence people, and there are documented evidences that a severe effect of electromagnetic waves on human being in terms of the skin responses, musculoskeletal pains, headache diseases, and many others. And our goal is to investigate this effect in cabin, in the vehicle, because it's even more severe because we have a metal cage, and this make these effects even more severe. Okay, so what's going on? Electromagnetic waves penetrate the upper layers of the human skin and interact with this capillary network in the epidermis, which is just a few millimeters below the skin level. And then they induce non-thermal effect on the circulating blood. And then the blood takes this effect into internal organs. And what it's doing into internal organs, that's a speculation, but we sure measured evidences that there are effects on the red blood cells. So all existing methods to evaluate these effects are basically inapplicable to real systems because they consider only static blood, okay? We take samples from the blood and you expose it to electromagnetic fields, and there are many studies who measure this effect, but this effect is not representative because in the human body the blood is circulating. And when the blood is circulating, there are effects that this system do not represent. So basically there is no work on really trying to investigate systematically the effect of electromagnetic fields on human being. So when the red blood cells flowing in the capillary system, they expose a shear effect, and shear effect affect the membrane of the cells, and as a result, they open different channels, the calcium channels and kalium channels, and the flow of different ions in and out the cell change their deformability and other factors which significantly affect the red blood cells. So there are evidences on mutations of the red blood cells that experience as a result of electromagnetic exposure, and our goal was to investigate these effects in the systematic laboratory experiments. So there are two major sources of electromagnetic fields. One is far field system that, for example, from the tower cell or from reproducers on the cars that stand on the rooftop, and then they induce the far field. And the second effect coming from the near term, where near field, when we have our cell phone very close to the head, or as many people take their cell phone and put it into a mouse. So they are very near field and they induce different effects. So we wanted to reproduce these effects and to investigate them. So first we looked on a near field electromagnetic exposure system. So that's the system we built. And the main challenge here was to reproduce the system with circulating blood, but to ensure that exposed volume of the blood remains the same. Because if the volume changes, all the effect is changed. So we designed these two cuvettes on the left and right, and then we have RF signal generator that connected to two electrodes within this cuvette, and they create electromagnetic field within the blood. Then we have two pumps that circulate the blood, and we test the blood from the second cuvette. In this way, we ensure that the amount of the exposed field is the same, and as you will see in a second that it's very important. And we also have very controlled temperatures conditions to ensure that this non-thermal effect, okay, because there are many speculations that the effect caused by the thermal effect, so it was very important for us to ensure that there are no thermal effects. We did electromagnetic simulations with CST simulation. We designed this cuvette, and the goal was to optimize the dimensions of this cuvette to ensure that we mutate the field that exists in real life, but within small laboratory conditions. And our main criteria was the uniformity of electromagnetic fields. Because if you don't have a uniform field, then you have many different effects, and we wanted to have a very systematic study. So the first experiment was to take just a monopulse antenna outside the cuvette, and as you can see in this chart, you see the distribution of the electromagnetic field within the cuvette, and what you see is that the field is non-uniform, especially at higher frequency. So we looked on all frequency range from 700 meg up to 5 gig to cover all frequencies that we have in our cellular communication and also vehicle-to-vehicle communication, all these frequencies that exist in the vehicle. So this system is not appropriate for our case. Then we used the dipole antenna outside the cuvette, and we again simulated the field within the cuvette with blood. So again, you see this periodic structure that the field is non-uniform, again, especially at high frequencies. Next, we move to the cylindrical electrodes and connected to this cuvette, as you see in the side, and it created a little bit more uniform field, but still the power flow on the right side was non-uniform, and it was especially on the connectors and less within the suspension within the cuvette. Next, we used plain electrodes to create the TEM cell to maximize or to minimize the variability of the field within the cuvette, and this system worked. Okay, in this case, we succeed to achieve both electric field, magnetic field, and also the power flow over the time to be consistently uniform within the cuvette. So in this system, we succeed to recreate the conditions, electromagnetic conditions, as it occur from the far field sources, but very near field conditions in the laboratory, very controlled temperature conditions. Okay, and we also looked on the uniformity of the field within the cuvette. So you see here the cuvette, and the blue lines show the cut of the electromagnetic field here, and all the different plots showing the field, actually the electric field within this cuvette, as a function of the size of the cuvette and the function of the frequency. As expected, you see that higher frequency induce more variations in the field, and the larger cuvette also creates larger variations, but still we were able to find that the diameter of 7.5 millimeter can provide us fairly uniform distribution of the field within the cuvette. Now we looked on how suspension level affect the uniformity of the field. So we tested different levels of the blood within the cuvette, and as you can see, when the cuvette is fully full in case 0, it has uniform field, but when the blood is degrading, you see more variability within the cuvette in case 3. So this explains why it was so important to build this complex system to ensure that when the blood is circulating, the amount of blood within the cuvette stay constant. Okay, so next we discussed how we're going to measure the effect of electromagnetic field, and we adopted the dielectric spectroscopy approach. And the idea in the dielectric spectroscopy is that when you apply the electromagnetic field on the biological system, they induce polarization. And this polarization, and if you imply the time varying field, the polarization will also change. So if polarization creates and change, we can monitor it. And there are theories that explain how the complex dielectric permittivity of the material can be used to measure this property of the polarization. So there was experiments and these theories are showing that electromagnetic field applied to a biological system create the polarization of the ions within the tissues. And this polarization can be characterized by measuring the dielectric property. So what you can see here is complex permittivity on the y-axis as a function of the frequency. And there is a specific peaks, the specific regions in this curve, which are called alpha, beta, gamma, that are very characterizing different materials. So we specifically looked in the area where the water is characterized because the water is the main component of the red blood cells. So we built this system and we designed the electromagnetic field with the whole frequency band from 0.7 to up to 5 giga. And we created a modulated wave with pulse duration 4 microsecond and duty cycle of 8 microsecond, which represents somehow the GSM transmission of 3G, 4G, 5G. And the reason for not using real transmission was because we wanted to investigate what parameter really affect the blood, okay? There are evidences that there are effects of the electromagnetic fields on the blood, but what parameter affected and how, it's unknown, completely unknown, okay? So we wanted specifically to identify which characteristic of the wave influence the blood. So in this analysis, we measured 4 parameters. Tau is a relaxation time, delta epsilon is the dielectric strength, sigma conductivity, and alpha is a Broding parameter. As you can see on this chart, these parameters represent how the variation of the relaxation time of the response and within the cell change over the time as a function of exposure to time varying electromagnetic field. So we measured these 4 parameters in experiments, and that's our results, okay? On the left, you see the controlled relaxation time tau. On the right, you see the relaxation time as after applying the electromagnetic field. So it's showing the statistically significant degradation in relaxation time. What does it mean? That means that when the cells, red blood cells, exposed to the electromagnetic field, they are deformating in some way. They are calcium channels opening, and their transmission of the calcium in between the cell changes. And as a result, they deformating, creating some mutations, and these mutations influence in some way our internal organs. How? Nobody knows, okay? But it's evident that there are mutations. And here summarized all these examples, and we had statistically significant t-tests showing that there are differences in this relaxation time. Now we looked more closely to investigate which parameters exactly in the electromagnetic field create this effect. And then we figured out that we actually are looking not very systematic yet. We still have 3 different fields created within the cuvette. We have reactive near field in a very close proximity to the electrode. We have radiated near field, a little bit farther away, and we still have a far field. So we still have a mixture of different modes within the one cuvette, and we wanted to design a more robust system. And then we built this system that looks like a case, just because we needed also to transfer it to Zurich. And we put the antenna on the top, we put the cuvette with the blood on the bottom, and we created a more uniform electromagnetic field. This is a new cuvette, so 2 pipes are used to circulating blood, 2 another pipes used for water cooling. Again, it's very important for us to ensure, actually nothing you can publish without ensuring that the temperature is stable. So that's the cuvette we designed, and we measured the uniformity of electromagnetic field within the cuvette, what you can see over here in the red and blue lines. So within the cuvette, the electromagnetic field is fairly flat for all tested frequencies. And we did a few experiments. So one experiment was to ensure that there is no temporal variations as a result of electromagnetic field, because we use very low, very weak electromagnetic fields of 10 dBm, and we ensured that there was no thermal effect with accuracy of 0.1 degree, meaning we're not heating the blood, we're just exposing it, something different happened, but not thermal effect. And here you can see the measured 4 parameters of the delta sigma, relaxation time, tau, alpha broadening of this relaxation peak, and permittivity sigma before the treatment and after treatment. And here again we had this statistically significant measure test, which proves that there are significant effects on the red blood cells as a result of electromagnetic exposure. Okay, so when next time you take cell phone, please remember that. Okay, and please try to use as less as possible your cell phone. So just to conclude that we have a very clear statistically significant evidences that there are effects of electromagnetic fields on red blood cells. We're currently working on building the models of that, and this effect is especially critical in elevators, in the vehicle, in all closed spaces. Okay, that's why on all elevators is written, please don't use cell phones. So the same should be written on the car. Okay, please don't use your cell phone within the car. Don't put your cell phone into the mouth. And we expect to see more results. That we're currently running large experiments with Hadassah bank blood, and in Zurich University. Thank you.
Hello. So thank you for the great talk. I wanted to ask, how about headphones, noise isolating headphones that all of us use? Is it the same thing or different?
Again, our goal is not to scare anybody, okay? Our goal is our goal is to purely scientifically measure effects within the cuvette, okay? What I can tell you that there are influence of the range between the emitter and biological tissues, okay? So every millimeter that you take apart is better, okay? So there are many speculations about. It's a hard question to answer, because there are some specific adjustment protocols, we send the cell phone that if it communicates with your device, okay, wearable device, it reduces some transmit power, okay. On one side you gain from this, but on the other side it's on you, okay. So it's still to be debatable. What I can tell you that all simulations and all what is written, proven when you buy any cell phone or any headphones, when it's written that it's proven. So yes, it's proven, but it's not very reliable proof because they only measure the power, okay, the average power. So the average power measurement ensures that you're not getting heated, okay, that's fine. But the effect that create these mutations in at least in red blood cells, are changes in the field, and nobody had measured it. Any other questions?
Igal, there are for the
vehicles, like people talking on the cell phones, on the trains, on the buses.
Exactly. So yes. So
Say that in close surroundings,
yes, it gets
amplifies the radiation.
absolutely yes. So similar as written on the elevator, כשאתה נכנס למעלית, don't talk on that should be the same in the bus and in the vehicle. No comment. Yes, please.
So I'm not sure I get the correct idea on my own. Okay, can I say that I made the WhatsApp call is much safer than I made the regular call?
Of course, just because you hold it farther away if you're doing the video call.
Thank you.
Okay, thank you very much.